Thank you. So let me first thank the organizers to organize this nice meeting. And I don't think I need this microphone. I guess you can hear me. Today indeed I would like to talk about some static and dynamical engineering of topological superconductivity. Basically, at the core of my talk will be the so-called Shiba-Rusinov states. So what are these beasts? Let's consider a magnetic impurity embedded on top of a superconductor, such as PB, for example. And let's consider the classical limit in which this magnetic impurity interacts with the substrate. So it means J times H larger than 1. And basically, in this classical limit, the impurity is acting like a local magnetic field and creates an attractive potential. So you get a bound states inside the superconductors with an electronic part and hole part, and which energy is given by these equations. And here alpha is the strength of the magnetic exchange energy and nu zero density of states. And if you increase the strength of the exchange coupling, then you have a change of the parity ground states. At low exchange, basically, your bond state is nearby the edge of the gap. If you push, then you have a parity change and the bands cross. So you go from even to odd crossings. So why these things are interesting? These are very old stuff discovered 50 years ago. Well, there is a resurgence of this interest to this physics because of they are good platform to engineering Majorana end states. And a set of recent experiments in Princeton, Berlin, Basel. And they they put magnetic atoms, such as iron, on top of lead, and they found evidences or signatures of zero bias anomaly at the edge of the 1D chains, which are interpreted as Majorana fermions. So, with some colleagues in Paris, we had more an engineer approach, let's try to understand if from a 1 to n impurities. So we first started with the single impurity and see what can we learn from the single Shiba states. So that's the outline of my talk. So basically I would try to convince you that I can use the properties of these Shiba in-gap states to learn properties of the host superconductors, which turns out to be quite interesting. And then I will move on to more cluster of magnetic impurities embedded in 2D superconductors and see that very interesting things come in. And if I have some time left, I will show you how to dynamical engineer 1D topological superconductivity. So let's start. So it goes back to 50 years ago. And these in-gap Shiba states can be parameterized by phase shift. And this is nice parameterization, which was put forward by Rusinov. Basically, the first term corresponds to the potential scattering term, and this is the exchange. Well, you can also write the asymptotics of the Shiba wave functions far away from the impurity. I wrote for the 3D and 2D component. Basically, there are three features. An exponential decay, which is given by basically by the sinus of the difference of phase shift, and you can recognize the current, superconducting current length scale here. There are oscillating patterns, which are Friedel-like oscillations, which depends on the phase shift. And you have geometric factors, which are just pure due to the 2D and 3D characters. So 1 over r decay and 1 of square root of r decay in 2D. Okay. So let's see whether we can test that. So the first experiment goes back to Yazdani 20 years ago. They had magnetic impurities in niobium. And basically, they compare the STM spectra with and without subtracting the magnetic impurity contributions. And from that, you can see these in-gap states popping up just when your tip is above the impurities. A message which is important to convey here is if you go slightly away from the impurity, let's say 10 angstrom, so 1 nanometer away, basically you are gone. The STM spectra is featureless. Okay, that's recent experiments my colleagues in Paris did, and they have magnetic impurities in niobium diselenides, which is a layer superconductor, so basically 2D material, and they've embedded impurities in there, such as iron, chrome, and manganese. And this is a 2D map, so at zero energy, so the IDV at zero energy in real space. And you see some nice flower here. And what is quite remarkable is the length scale. The scale is about 20 nanometers. So previously I showed you some signature of an in-gap states about a few angstrom. Here there is a factor of 20 basically. So let's zoom in. And if you zoom in this flower, you see even some interference fringe in the arms of the flower. And they indeed correspond to this in-gap. So let's make a cut and see. So you have some interference patterns indeed. A big one associated to this to the larger component, the electron one, and some phantom one which is laying behind. So how can we understand that? So we do expect some oscillation patterns which are related to this interference. And can we have a closer look? So this is the IDV as a function of the distance when we moved away from the impurity. And let's try to, well, we can describe and fit actually this data with the exponential decay and the sinusoidal oscillations. And if you look more carefully, you may see that the electron and hole part far away from the impurity have a pi phase shift. So when the maxima of one corresponds to the minima of the other one. So, well, can we understand that? Yes, indeed. If you look at the position of the Shiba states inside the gap, they are basically almost in the middle of the gap, which correspond to a phase shift here equal pi over 2. So delta plus minus delta minus equal pi over 2. And therefore, when you measure the density of states, so the square of that, it corresponds to delta plus, you will measure the difference of phase shift twice delta plus minus delta minus, so pi phase shift, which is indeed what is measured here. So basically, you can put in correspondence the positions of the peak inside the gap with the oscillation pattern far away from the impurity. Fine. So what can we learn from that? It means that we have a very good spatial resolutions of these in-gap states. So why not using them as a probe of the properties of the gap of the superconductors? So typically, and what would be the motivation to do that? So there are many new 2D superconductors popping up these days, and with eventually topological properties. And can we use these Shiba states, bond state spectroscopy, to extract some in situ some properties of these anomalous superconductors? And particularly, why not measuring the spin-orbit interactions in situ? Okay, how to do that? Let's, to see that it's possible, let's consider a simple model Hamiltonian in which I have a S-wave superconductor plus some Rashba spin-orbit coupling, and I'm in 2D. And ideally, you can solve, you can solve your bond state equations and write all your observable. You can do that analytically if you wish, but let's see, for example, let's consider 1D just to see what to expect. So in 1D, in presence of a spin orbit, your parabolas are shifted by the spin orbit coupling. So you get these two parabolas. And what you're probing, actually, with STM, what you would be able to probe is some quasi-particle interferences. And here you have many sorts of scattering which are possible. And the most interesting one is between this band, the plus band and minus band, which involve the spin orbit momenta. And therefore, if you're able to look at the quasi-particle interference, you may trace back to the spin orbit momenta and by the Friedel oscillations. So this is a pure, there is no superconductivity in there. So what survives in the presence of superconductivity? So what we calculate here, so this lambda is the strength of the spin orbit. P, it's the momentum in 1D. And what is plotted is spin-polarized spectroscopy assuming a magnetic impurity along the z-axis in the 1D wire. So this is a polarized density of states, if you wish, and this is the gap. And you can localize, indeed, at the fixed value of the spin orbit. Then you have a strong signal mimicking, from which you can directly extract the spin orbit coupling. And this is for the z response. So if you are able to measure the Sx observable, then these two guys will be, this one will be spin up, this one will be spin down. So this was for 1D. You can do the same in 2D. So this is again the Fourier transform of the in-gap Shiba states, spin resolved, and I assume I have a magnetic impurity along the z directions, for example, or along the x directions, and I look at different answers. And this is Px, Py, so Fourier transform of the 2D map, and you can again you have a strong features whose position is related to the spin orbit coupling. So, well, these days, I mean, spin polarized measurement with STM is, many groups are producing data in that directions. We may hear some more this week later. So I hope, at least, I'm convinced that, well, with the very good resolution we can reach in 2D, this is most likely doable to very high precisions. Well, there is much more you can do. For example, we did this kind of calculation for different problems. We look at the Shiba state spectroscopy for pure P-wave superconductors and pure S-wave and so on and so forth. For example, even if I did not tell you before, well, you will be convinced that this feature, which is a Fourier transform of some in situ in-gap states, has some P-wave character, even if you don't know what it is. So you can really goes back to the orbital nature of the P-wave superconductor just by this Shiba state spectroscopy, and also you may differentiate the nature of the D character. So it can be if you have a D vector characterizing the superconductor in plane, out of plane. There are many things you can really extract and trace back by reverse engineering from this Shiba in state spectroscopy. Okay, this was, I want to convince you that indeed, spin polarized spectroscopy is a very interesting tool, which is sensitive to the spin orbit, and also it allows to distinguish many properties of the in-gap superconductors, such as the degree of P-wave character, but also what type of P-wave do we face. Oh, okay. Now I want to move on and to see what's going on when I put many impurities. And actually, the strategy we had in mind initially was we wanted to understand dimers, how dimers of magnetic impurity interact. So, but it turns out the strategy the experimentalists will do, okay, if we want to have dimers, let's increase the density of impurities, and by chance we'll get some dimers, maybe. Well, actually that does not work that way. They increase the density of impurities and they form clusters. So, and typically, this is the system they consider. It's lead monolayer, which is superconducting at low temperature, and they have cobalt, and this is the deposit adsorbed on a silicon 111, which is a insulating substrate. And they increase the density of cobalt, and the cobalt at some point form huge clusters, well, huge at the level compared to a single atom. These clusters are about from 5 nanometer to 10, 20 nanometers. So they contain from 50 to a few hundred atoms. So a priori, this is an interesting system to look at. We have a 2D lead superconductors. We have some cobalt, which is supposed to be magnetic. So we have some magnetic below. And since this is a purely 2D system, we break strongly inversion symmetry. We do expect a strong spin orbit coupling. So this is what they observed. Again, a 2D map, real space, at zero energy. And you see such huge and nice ring, well, about 5 to 10 nanometers of diameter. And let's see what happens when we increase the energy. So actually, these rings, they split. Maybe I forget to say that these rings are, well, they happen only on top of the clusters, not everywhere, obviously. So when you increase the energy, they split and eventually separate, and this is almost the edge of the gap. So let's go to a 3D representations. So this is what I showed you before. And let's make a cut. And if we make a cut, that's what we observe. This is the energy, the gaps. And at zero energy, you have a degeneracy of these dispersive in-gap states. And eventually, they split, and they become tangent to the in-gap. So how to interpret these features? Well, we took the simplest model as possible. What are the ingredients? We assume the cobalt clusters provide you some large Zeeman field. We assume that we have some Rausch-Bach spin orbit term, which is also producing some triplet superconducting order parameter, and which is subleading. Most of the superconductivity is coming from a standard S-wave character. So it turns out that that's the minimal model we put forward phenomenologically, the spectrum of which is already complicated enough. Let me show you the phase diagram. If I switch off the spin orbit, basically we have three phase, and two new energy scale comes in. So this is the phase diagram as a function of Vz divided by delta S, the Zeeman term, and delta T, the degree of triplet pairing. You have a trivial phase. Well, then if you assume you have a strong triplet character, you have a topological transition from a trivial to helical phase, where you have two H states, helical ones. If you instead increase the Zeeman field, you have a closing of the gap, and you go to a chiral topological phase with a single dispersive Majorana H states. So this was to obtain this phase diagram. We assume a purely homogeneous Zeeman term everywhere. And if this was obtained for alpha to 0, well, the topology of the phase diagram remains qualitatively the same if we have a strong spin orbit. Now you can go from the trivial phase to the chiral phase. Fine. So how to use this kind of phase diagram to interpret the results? Well, what we did, we assume now an inhomogeneous Zeeman term, which is now on some only in a region of space on top of the magnetic clusters. And it means that, for example, far away from the cluster, we are on top of a cluster, we're in the chiral phase, for example, and when we move away, we are going to the trivial phase. So what do we expect? We do expect a topological transition in real space. Since here we are topological, so far away from, on top of the cluster, and far away we are trivial. And this is what we obtain by exact diagonalizations. Indeed, you see some topological transition in real space with some quasi closing of the gap, and you see some left over from this chiral Majorana dispersive chiral H states. So that's and when we add this helical part, so let's say when we move from this point of the phase diagram to this point, so with a little bit of a helical phase, then indeed you recognize some features that were obtained experimentally with this X shape of the spectroscopic in-gap states, and far away, indeed, when we move away, the degeneracy is lifting and recover these circles. Okay, there are some disagreements also. They did observe a perfect, well-defined gap, as we do have some, almost a closing of the gap. So it's not perfect, but that's one simplest model we can put forward and seems to indicate the topological transition in neural space. That's not the end of the story. Because a priori, if we want to interpret these dispersive in-gap states as dispersive Majorana bound states, what you would like to do is to localize these Majorana bound states. So for that, how to localize these Majorana bound state in 2D, you need vortices. Can we observe some kind of vortices? These are other data they obtained recently, where you reckon same device, but for larger cluster size, typically 10, 20 nanometers, you have some kind of a fuzzy ring here and a huge peak in the middle. Let's zoom in. Indeed, spectroscopically, far away, you recognize your well-defined superconducting substrate, nice gap. On top, in the middle of the cluster, you have a huge peak, and in the intermediate positions, almost the same as that one. And in this fuzzy ring, you recognize again a zero energy smooth ring. So density of which, if you will be able to integrate the density of this fuzzy ring, you will recognize there will be a huge density which will also match that one, almost match that one. That's a 3D plot. And when we do a cut, there is a huge peak in the middle, then nothing, and then we recognize the zero energy peak. So it seems that these are recent data, not yet in the archive. And well, they have some kind of evidence of at least zero bias peak, huge, and which seem to indicate that we are facing some kind of a vortex or vortices which are stabilized by huge clusters of magnetic atoms. So we are trying to understand that, and in the few minutes which I'm left over, well, I will just flash some, or just give you the maybe the idea is how to engineer. So this new platform, how to use this new platform. So basically, what I show you, either we use chains of atoms on top of superconductors, and we will hear more this week by Yazdani about that. And you can obtain the P-wave superconductivity that way. The best drawback, unfortunately, is that you cannot really control the properties of your Shiba state. You need some handle. The only handle you would have is magnetic field. But for that to be efficient, you need, well, it's not so easy. So we came with the idea to, well, why not irradiating or driving these magnetic impurities on top of the superconductors, so such that we can make them precess. And if we make them precess, then, well, we can work in the rotative wave. You just undo the precession in going to the rotative wave transformations. And basically, you can act with some ineffective magnetic field. And you have lots of interesting physics that comes in. And basically, the main message I want to convey is that you can control the topology of the system by the control of the driving. But I won't have time, and it's time for me to conclude. So I tried to show you that these magnetic impurities in superconductors are good, interesting platform to engineer new topological superconductivity. Well, first, you can use them to learn something of the property of the host superconductor by this Shiba state spectroscopy. Also, you can create new and interesting superconductivity by mixing these magnetic impurities, forming clusters inside 2D superconductors, and with an interesting property that we're still trying to understand, such as vortices. And the last idea I want to convey is that dynamical engineering, well, which may be still far not yet reached, but is an interesting tool, I think, to get a new handle, new knob to control these topological properties. And let me thank my precious collaborators, especially the experimental group in Paris with whom I've been collaborating the past years, so led by Tristan Gren and Dimitri Rodichev, my PhD, Vardan Kaladzian, and some other PhD. And thank you for listening.